So with the speed, do not forget that the concept behind what we are doing is that for a horizontal road which is unbanked or which is not erected at any angle, we'll do banking of road today. For unbanked road, velocity is equal to square root of the coefficient of static friction between the road and then the gravity. And for the car to make, so for a car to make a turn, for a car or any automobile to make, Nathaniel,
Sorry that you the assignment you sent in the group.
yeah.
Are we to do it now?
Oh no, it was
Okay.
the very assignment you submitted. Okay. Oh, Nathaniel,
Okay.
you did not submit yours. I think I remember you did.
I did submit.
Okay.
Yeah, I did submit
We are
mine.
just reviewing some observations I made. Okay.
Okay,
So
thank you.
okay. So for a car to make a turn without skidding, please mute yourself if you haven't done so. So for a car to make the turn without skidding, the permissible or the maximum velocity must be less or equal to this mu rg, meaning that if V max is greater than square root of mu rg, the car will skid off from the circular track. Okay. So with regards to the assignment, for one same road whose conditions changes with time, when dry, when rough, is the same road, but we are looking at different conditions of dryness and then wetness. So basically, it's about the same road with a constant value of radius. And then gravity, whether the road is large or the radius is smaller or whatever, gravity is the same. So that is why I gave you this relation that V, therefore, for same road, when one is dry and one is wet, V dry is directly proportional to the square root of the nature of the surface. For V wet is directly proportional to, this is dry, D, and this is mu when wet. So when we take a ratio of the V's or the two situations, one when dry and when wet, we have VD over VW equal to square root of mu D over mu W. Here we equate we put an equal to sign because the constant of proportionality, which is Rg, okay, will cancel out in both situations. So we do not repeat V is equal to mu square root of mu Rg and divide by, because it's the same road but two different conditions. R and G simply varies. Okay, so the constant, which is Rg, will cancel out, and we'll come back to this. You don't need to quote the equation, substitute your figures before you do that. That is one quick observation I have. So with regards to the question, we are told that when the road is dry, its velocity is 20. So Vd is 20 meter per second. Okay, if the road becomes wet, its velocity is 10 root 2, 10 root of 2 meter per second. And we are to find the ratio of the coefficient of friction for dry and then wet. So it means we are looking for what is at the right hand side. Okay, to do that we need to eliminate the square root sign. So we square both sides of the equation. So we have mu when dry over mu when wet to be equal to 20 squared over 10 root of 2 squared. This is 400 on 100 times 2, which is 200. So when you make the division, you realize that you have 2 over 1, implying that the ratio mu d is to mu w is equal to 2:1. Okay, in ratio, if the denominator is 1, do not just write to indicate 2:1. So that does it for the first question. The second question, a string can withstand the tension of 100 Newton, the greatest speed. So this is equating the tension in the string to the centripetal force, which is mv squared over r. Okay, and we have to find the maximum speed. So the tension is 100. The mass is 1 kilogram. Radius, which is equal to the length of the string, is 1 meter. Therefore, 1 kilogram divided by 1 meter will be equal to the same value. Therefore, V is equal to the square root of 100, which is 10 meter per second. And that does it for the greatest speed. So V greatest, that's all. Question 3, the same question of dry road and then wet road. On a dry road, the maximum permissible speed of a car in circular path is 10 meters. So this is, if we take the ratio, 10 meters over, if the road becomes wet, it is 5 root 2. 5 root 2. And we are, if the coefficient of dry road is x, then, so this is equal to the square root of dry, which is given as x, and then when wet, we don't know, so mu wet. So we have to find mu wet. You get rid of the root sign and you have x over mu w, also giving us 100 divided by 25 times 2, which is 50. Okay, when we reciprocate this mu w on x, we have 1 over 2. Oh, we are actually looking for, okay, mu w. Therefore, mu w is equal to half times the coefficient of static friction of dry road, which is x. As simple as this. Okay. So it is not so difficult. Any questions so far? Any questions so far? All right. Then let's continue our journey. So far we have realized that for an unbanked road, for a curvy road, a curvy horizontal road, that is what we are actually calling as unbanked. It is not banked. You will later understand what I mean by banking of road. For an unbanked road, on an unbanked heavy road, okay, I think unbanked road will do because we bank road at where we have heavy, okay, heavy parts. We have noticed that the maximum permissible speed depends on friction and the radius of the road. So when friction varies, when the coefficient of static friction of the surface decreases, as in when the road is rainy. Julian, please mute yourself. When during rainy season, okay, in Europe and America, when during snowy conditions, it will reduce friction on the surface. And so it means that we need to reduce speed. But we cannot always depend on friction to make the turn because frictional force is affected by external factors such as rain, okay, rainy conditions and snowy conditions. For that matter, because we cannot always depend on friction, there is an intervention where cars can be able to make a turn without depending on friction. In this case, when there is friction, yes, cars can make the turn. When there is no friction, cars can equally make the same turn. So there is an intervention by road designers which caters for, okay, the ability of cars to make this sharp turn even when there is no friction, as in during rainy and snowy conditions and all other external factors that affect friction on the surface of the road. Class, are you with me? Class, are you there?
Yes, please.
So
Yes, sir.
that intervention where drivers or motorists do not depend on friction absolutely to make a turn, okay, brings about a concept which is known as banking of roads. Banking of roads. Please, this is not the financial sector banking. This is a physics and engineering banking applicable to roads. Before we go to banking of roads, let me bring your attention to what we often observe in MotoGP, motor races, and then bicycle racing. You see, if you have ever watched MotoGP before, when motorists are making a sharp turn, okay, when they are riding and they are making a sharp turn, the motor and the body of the rider is bent at an angle. Please, class, have you made that observation before?
Yes.
Yes, sir.
So
Yes, sir.
the whole body of the motor is bent at an angle. What they do is not stylish thing, but they are actually doing that because of friction, or because of, instead of friction, let me use centripetal force. They want something extra to give them centripetal force, which can be used to make that sharp turn, because It's a competition. If the road is curvy and you want to turn, you cannot afford to reduce speed. By the time you reduce and cross, you have been overtaken. Yet they don't want to, they always want to outsmart their competitors. So to do that, they decide to bend the motor. As they are bending, the idea behind it is to give them an extra edge which would enable them make that sharp turn with that top speed. Okay, so motorists also bend a curve. So this is about bending of a cyclist. Bending, before we look at banking of roads, bending of a cyclist. So this is a cycle. I'm trying to draw a cycle or motor where the rider bends the motor at an angle. Please, when you come in, mute. Now, let me mute all. Let me mute all. So this is my design of motor or a bicycle. I think it's better than what can be drawn by a lot of you, but I'm not mentioning names. So to make the turn, the cyclist decides to turn the bicycle or the motor at an angle theta to the vertical line. There's the whole curve. The road is curvy. Yes, pardon me for my curvy road. It's not the best of roads, but this is what my money can build. Okay, so the cyclist bends the motor or the cycle within the center of the curve. So the center of the curve is somewhere here. From the center to this point, obviously, is the radius of the road. Now, we have the weight of the car, which is always perpendicular to the road acting here. So mg is the weight of the car. Once the cyclist bends the motor, it changes the normal reaction. The normal reaction always follows the angle of bend. So this is the normal reaction force N. We can also use R. So we seem to have this, the vertical, then the normal reaction acting on the cyclist. Between the normal reaction and then the vertical, I mean this vertical, this one, that we have the bending angle theta. This is N. And in physics, whenever a vector quantity is at an angle theta, if it's perpendicular, we don't have problem. The whole quantity would act along the vertical. But the moment it turns at an angle, we must resolve this quantity into its vertical component and its horizontal component. So this will be the vertical component. I think I need to use a line to make it straight. The vertical component of the normal reaction, and then the horizontal component will be on the straight line. So when we resolve the normal reaction N of the motor, we have the vertical component giving us N sine theta. If you are at C, if we take sine of theta, sine is the opposite. The opposite is what we are looking for. Opposite to the angle divided by the hypotenuse. The hypotenuse is the normal reaction N. So if we make what we are looking for the subject, we have N sine theta. N sine theta. Okay, and that is this component I've indicated. The vertical is always perpendicular to the horizontal. So the horizontal component, on the other hand, this part would also, to get the horizontal, we need cosine. So cos of theta is equal to the adjacent, which we are looking for, divided by the hypotenuse, which is the normal reaction. This is therefore N cos of theta. So this component, we have the vertical component acting here, N cos theta. So when we bring it to the diagram, we have N cos theta here. We have N sine theta here. But then vectors are equal wherever they are. And so instead of writing the vertical component here, okay, I would love to bring it on along the radius of the road. So we have N sine theta acting here. Class, are you okay up to this stage? Are we okay up to this stage? Before I continue,
Please, can you come again?
I'm asking if you are okay up to this stage.
So, like, can you come again from the sign resolving of the
So
vector?
we have the whole cycle bent at an angle to the vertical. Along this line, we have the normal reaction N. The angle made with the normal reaction to the vertical is theta. So we are resolving to get the opposite side and then the adjacent side. Okay. And when you use the trig ratios, of course, if you want opposites, you need to use sine of the angle. So sine of this side, I'm calling as the opposite. Let me represent that by x. Sine x is equal to x over n. Therefore, x is equal to n sine theta. And this side, y, it would be cos of theta, which is equal to y over n. If you make y the subject, y is equal to n cos theta. Okay. And so that is it with the opposite side of the reactional force and then the adjacent side. Please, are you fine now?
Yes, please. Thank you.
Okay. When we look at the component vertically, we realize that the n cos theta component is balanced by the weight mg of the bicycle. So n cos theta acting vertically up, mg acting down, equation 1. If we look at the horizontal component, we see that the n sine theta component is unbalanced. It is not balanced. But because its direction is towards the center of the circle, we equate it to the centripetal force mv squared over r. So when the cyclist or the motorist is riding and then he or she bends the motor or the bicycle, okay, the extra component which enables him to make the turn with that top speed is provided by the n sine theta component of the normal reaction of n. Okay, that is why we are equating mv squared over r, which is the centripetal force, to n sine theta. So when the cyclist is making that top speed and still want to make the turn without reducing speed, he will tilt the motor at an angle. By doing so, all that he is doing is that he wants to augment the centripetal force, okay, by making sure that this n sine theta component of the normal reaction adds up to the frictional force on the surface, because the friction alone cannot help him make that turn unless he bends the motor. So what they do is to augment the centripetal force. And what does that? What does that is the n sine theta component of the normal reaction. So it is take note that the n sine theta component of the normal reaction provides the centripetal force. Are you okay? Class, are you okay?
Yes, please.
So, I'm coming. So in this case, whether the road is wet or snowy, because he has that ability to turn the motor so that he would the sine n sine theta component will provide a centripetal force, he will still be able to make the turn, that turn. Please, if you have any question, quickly ask before I continue. So riders, motor riders, bicycle riders, and even aeroplanes also make that turn. They make that turn to negotiate a sharp curve with a top speed, but not that they don't turn it anyhow. They will turn the motor when they are riding at a top speed and they still want to make that quick turn. So they clearly do not want to reduce speed, yet they need to make a turn. And before you can do that, you need to turn the motor or the aeroplane at an angle so that it provides the n sine theta component, which is equal to the centripetal force. The centripetal force. So looking at equation 1 and equation 2, let's divide equation 2 by divide equation 2 by equation 1. So divide equation 2 by 1. We have n sine theta divided by n cos theta equal to mv squared over r, also divided by mg. So we see m canceling out. We also see n canceling out. Class, what is sine theta over cos theta? So this is tan theta. We have tan theta equal to v squared over rg. Let's make v the subject. V is equal to RG times tan of theta. Meaning that taking the square root. Meaning that, and V is the maximum speed. And here the maximum speed is directly proportional to the radius of the road. The maximum speed is also directly proportional to the square root of the tangent of the angle of tilt. As for gravity, it is constant. Meaning that if you are riding a motor or bicycle and the radius of the road is large, the speed, you can increase speed. Okay? If the radius of the road is small, nobody should tell you to reduce speed, else you can't make that turn. You will definitely skate off the circular track. Then the maximum velocity also depends on the tangent of the angle. Meaning that if you are moving with a top speed, then the angle through which you must bend the bike must be large. That is why MotoGP, the riders turn even to the extent that their whole body is touching the ground. Please, class, do you observe that?
Yes, please.
Yes, sir.
So look at the speed they move with. So if you want to still make that turn with that higher speed, then your angle of bending or tilt must be large. And so you must turn the motor inside the curve almost to the point that your body is touching the ground. And this is done by experience. If Mr. Edia tries it, I would somersault. Okay, so it's a skill that must be adopted. So that is why that they make that turn. Aeroplanes also do that. Whenever they want to make a quick turn, the pilot turns the whole plane at an angle. Some of you will become pilot, and you remember Mr. Edia that he said it, that one day you'll be turning the plane. Okay, so this is the reason behind bending of the motorcycle during motor racing. So by this formula, motorists are making a turn without depending on friction. I'm not saying friction can't be there. Friction can be there. But in the case where the road is slippery or snowy, motorists can still be able to make that turn without skidding. If you have any question, quickly ask before we continue. I'm also taking notes of attendance, so please, if you have a question, you can chip it in whilst I take notes of attendance, okay? Mommy, I asked your question. Elizabeth, you too.
Yes, I'm okay.
Julian, Nana Safo. Yeah, my first question. Okay, I'm coming. So this time, when you see MotoGP, please watch them well. Just enjoy their skills. At least you now understand why they do that. So, hey, Jojo, ask your question. So
No question.
my question is that if they do all this, and some of them can still skate off the circular path. Why do they skate? We see a lot of them turning the motorbike. All right. Yes, they sometimes skate off from the circular path. Why do they skate? If you are not asking question, I'm asking you.
Yeah, sir.
Mm-hmm.
I believe that like there's a maximum angle to which they can tilt without skidding.
Mm-hmm.
So some of them may tilt beyond that angle, and that's what caused them to skid.
Jojo, nice observation, but I disagree with you. More views. More views. Nathaniel.
So please, to me, I think it's maybe they can't maintain this thing, a stable velocity.
They can't maintain a stable velocity. Okay.
And maybe some of them to their leg or maybe some parts of the motor touches the ground, which creates an opposing force for them to somersault.
Okay. Okay. Well, noted and accepted. Okay. The reason why sometimes they fall or skid is that you see the speed v squared is equal to rg times tan theta, meaning the speed is directly proportional to the square root of the tangent of the angle of tilt. So every speed goes with a certain amount of turning. So if you decide to move at a certain speed, and during the course of making that sharp turn, you cannot produce the corresponding turn, then the obvious decision is that reduce speed to make that turn. Because if you are also turning, okay, then you must be careful, just as you said, when your body touches ground, it will create extra force and it can topple. It's like collision. Okay, so if you can't make that commensurate turn, reduce speed. Okay, it's not by force that, no, because you are turning your body and the bicycle, you must move with any speed. The speed goes with the angle of tilt. So you control the speed, the rider controls the speed. So if you are moving so much and you are not able to make that turn, which will commensurate the speed, you will certainly skate off. So that is why. So some of them, when they are turning and they are moving so much, when they get to that curvy part, they will reduce speed a bit, make that turn, and when the road is straight again, increase the speed. But some people, they believe themselves and they are by. And this is some of the reason why. And usually, if you're also turning and you are not careful and your motor hits another, then there will be extra force acting on both bikes. And if you are not careful, controlling the bike at that speed becomes difficult. So that's the reason why. Please, is it understood?
Yes, please.
Okay, so let's move to banking of roads. Banking of roads. Road bank. Crystal Edward. Priscilla.
Sir.
Is the
Ten.
network stable now?
Yes, please.
Okay. Banking of roads. With cars, you see, because for motors and bicycle, I say this is two-wheel. So if you are riding and you turn your body, it will turn the bike or the bicycle as well, or the motor. But if you are in a car, driving a car, and you want to make that sharp turn yourself in a car. You, the driver, can decide to turn yourself in the car. But as to whether it can turn the car is the issue. Are you with me? Imagine a driver who wants to do what motor riders do by turning himself in the car. You will turn and fall, but the car will not mind you. Is that okay? So because of the architecture of the car, the driver cannot turn in order to give it that angle and that extra centripetal force which will make the turn. And so in curvy roads, to do that, road architects or civil engineers build the road and then tilt it at curvy points for them. And when you are riding on a road and the road is tilted, of course, the car will naturally also tilt. Okay, so the road is designed in this manner. One edge of the road is raised towards the center so that it looks like an inclined plane. So one end is raised, the end of the road which is raised H. It is tilted at an angle theta. So this is a curvy road. So this is a curvy road, but the road is tilted. Okay, it's tilted at an angle. This is the whole width of the road. I want to share with you a video of a banked road. So give me a minute.
Banking of Roads 01.
So
Objective:
listen to it.
to understand the role of friction at circular turnings and banked roads. Maximum allowed speed while taking a turn. When a car takes a turn, each curvilinear section of the turn can be approximated to be an arc of a circle with a certain radius. A centripetal force must act towards the center of the arc to enable the vehicle to move along it. This centripetal force is provided by the static friction of the surface the car is moving on. Normal force N balances the weight of the car mg. If the coefficient of static friction is mu, the maximum frictional force which can act towards the center of the arc is mu mg. While making a turn, if the velocity of the car is v and radius of the arc is r, the centripetal force acting on it would be equal to mv square by r. For the car to make a safe turn, the required centripetal force should be within the limit of static friction, which implies that the velocity of the car should be such that it satisfies the relation mv square by r is less than or equal to mu mg. In other words, v should be less than or equal to the limiting value root over mu rg. Moves with a velocity greater than the limiting value, it skids away from the center. Banking of roads. We cannot always rely on friction as it depends on external factors such as rain or frost, which significantly decreases the value of static friction. To avoid skidding of vehicles at turns, the outer edge of the road is raised up, which is called banking. Suppose surface of the road at a turn makes an angle theta with the horizontal surface. This results in the horizontal component of normal force, n sine theta, acting towards center, providing the necessary centripetal force at the turn. Friction is not taken into consideration here. Therefore, n sine theta is equal to mv square by r. The vertical component of the normal force balances the weight of the vehicle. So, n cos theta is equal to mg. From these equations, we arrive at the equation tan theta equals to v square by rg. Thus, v is equal to root over rg tan theta. This equation gives the speed which, in the absence of friction for a given angle of inclination and radius of curvature, would ensure that the vehicle remains in its designated path.
Mommy, I'm coming in. Let it end. I'll give room.
Is known as the rated
Questions,
speed
okay.
or balancing speed of a turn. Rated speed of a curve does not depend on the mass of the object. Summary. The maximum speed with which a vehicle can move without skidding while taking a turn on a horizontal road is root over mu rg. The maximum speed with which a vehicle can move without skidding while taking a turn on a banked road is root over rg tan theta.
So this is it with banking of roads. I'll go through it with you. So, Mamia,
Please, the first question is that why do they do they do the bank roads like for the public use, or they only do it for like those racing activities
it's for public.
or
So
anybody?
it's for public use. It's on our roads. So these days, whenever
Okay.
you are traveling, okay, and you get to areas where the road is curvy, watch. Okay. When the road is so curvy, the road is banked so as to there. I'll give reasons why the roads are banked. So it's for public and for MotoGP and then Formula One.
Okay. And please, there was this formula tan theta is equal to v squared over rg. How did they get the tan theta? Because they were talking about cos theta and sin theta,
And don't
and
worry,
it suddenly changed to tan theta.
I'll take you through. Hey, but Mamia, have you also forgotten that when we're looking at the motorists bending, the cyclists bending, okay, bending up by cyclists, we also saw tan theta.
Yes.
So it's the same thing, but I'll take you through, so you don't worry.
Yes, please.
Is there any other question? Okay, then let's move to my explanation. Okay, so banking of roads is an architectural design where roads are built in such a way that it is tilted towards an angle, towards the center of the road. Okay, so banking of road is an architectural design where roads are built such that it is tilted at an angle towards the center of the road. Okay, or where the outer edge of the road is raised at a height. So either you are tilting it at an angle theta, or the outer edge of the road is raised at an angle. This is the concept of banking of roads. Somebody is complaining of having difficulty in joining. Oh, it's the same link. Tap on the link and it will send you to the class direct. Okay, so this is the rationale behind a. Now it is done for these purposes. Purposes of banking of roads. One, it is done for to ensure that cars do not skid off the road, so that cars do not skid off the road during rainy and snowy seasons. Rainy and snowy seasons, because in those seasons friction is so less, and if friction is less, then the chances of cars being skidded off the road is high. So at curvy roads or points, the roads are banked in order to prevent that. So it is actually for, one of it is for safety reasons. Now it is also done to ease movement. This is because when roads are banked, motorists have the chance to travel at a certain speed which cannot be moved on when the road is not banked. So if the road is banked, there is that maximum speed which motorists can travel on, and this speed cannot be traveled with when the road is unbanked. If the road is unbanked and drivers move with that speed, they can skid off from the circular track or path. So when roads are banked, it is done to ease movement because you have that chance to travel at a greater speed. Okay, so I'm explaining. So please, you must note it and then use it accordingly. It also depends. It also reduces wear and tear of car parts such as the tire and other parts of the car. So it reduces wear and tear on car parts and the road. And the road. This is because when the road is banked, there is the point where there wouldn't be dependency on friction. So if we are not dependent on friction to make a turn, then friction brings about wear and tear. Okay, so it's like moving away from friction a little bit. Okay, so let's go into. So these are the purposes of banking of roads. So this is a car on a banked road. My model of a car. So when the road tilts, the car would automatically tilt as well. We have this as the this line is the weight of the car. Weight of the car, mg. Then the normal reaction on the car always follows the surface. The normal reaction is called as such because it is always perpendicular to the surface. So when the surface of the road tilts, the reaction also tilts and must be such that it is perpendicular to the surface. We use N. When we extend the normal reaction line, we have this. So there's an extension of the line, the normal reaction. Now, on an inclined plane, if the angle of tilt is this, the angle between the normal reaction line and the weight also is equal to the angle of tilt. So if on an inclined plane, when you tilt it by an angle theta, this angle between the weight and then the normal reaction is also theta. I don't know if I've proven that with you before. If this is theta, this angle would also be theta. Vertically opposite angles are equal. Please, are you okay?
Yes, please.
Okay. Now, we have this normal reaction N. the normal reaction line here, tilting at an angle. So just as we saw, it is tilting at this angle. So we have this theta. This is n. We must resolve it into its vertical and horizontal component. This component here, which is the same as this, obviously will be n cos theta. This vertical component, which is also here, would also be n sine theta. So when we resolve this, we have this component as n cos theta, similar to what we've done. That's why I'm not going through it. And then this horizontal component, which is also n cos theta. N sine theta. But because of equal vectors, we want to bring it on the car. So instead of having n sine theta here, we are bringing it here. Okay, vectors are equal no matter where they are, if they have the same magnitude and direction, and they are. So this is also n sine theta. Just similar to what we've done before. Okay, just similar to what we've done before. Now, please, is there any question here? Is there any
Please,
question?
can you? Okay.
Okay, Mami, okay.
Please.
Okay, then okay. So we just resolve the normal reaction into its components. Now, when we look at vertical components, the n cos theta is balanced by the weight of the car, mg. Then the n sin theta is unbalanced, but because it is directed towards the center of the curvy road O, we equate that to the centripetal force. So when the road is banged, it is the n sin theta, this component of the normal reaction n provides the centripetal force. That is why we are equating it to mv squared over r. It is no different from a cyclist making that bend. So we have n cos theta being equation 1. This is 1. And then n sin theta being equation, this is mv squared over r, equation 2. When you divide equation 2 by 1, Mamiya, you have n sin theta divided by n cos theta, which is equal to mv squared over r divided by mg. So just as we've seen before, m will cancel out, the normal reaction will cancel out, and Mamiya, sine over cosine is equal to tangent. Tan theta. This is because sine, the ratio of sine to cosine is equal to tan theta. Please, is everybody okay?
Yes, please.
And
Yes,
this is equal to v squared over RG. And when we make V squared the subject, we have RG times tan theta. V is therefore equal to the square root of. Before that, before I go to V, please, when you look at what we have, if the width of the road is W, from this point to this point is also W, then we can also equate tan theta to be equal to H over W. H over W. I mean, from this point to this point, if this length is W, then the same tan theta can also be equal to H over W, where H is the height, vertical height of the road, and W is equal to the width of the roads. Because this is necessary, because sometimes you wouldn't be given theta directly, but you'll be given H and the width of the road. And you can also use this to find the banking angle before you use that to solve for the velocity. So square root of RG tan theta. This is the maximum velocity, meaning the maximum velocity should be less or equal to the limiting value of this. By this, it means that V is directly proportional to tan of the angle. Okay. So look at this equation. If I want to move at a speed, maybe 36, using tan theta is equal to V squared over RG. If I want to move the car at a speed, maybe 36 meters per second, when the radius of the road is maybe 1 meter, R is equal to 1 meter, I can put these values into the equation. Of course, J is equal to, it's a constant, 10 meters per second squared. So if you want motorists, the maximum speed on the road to be this value, then the engineers would use this formula to determine the banking angle theta, so that motorists can move at this speed. If this speed is not enough for you and you want motorists to travel at a greater speed, then maybe 100 meters per second. When the radius of the road is 1 meter, substitute the speed into it, the radius, and you can determine the banking angle. So they will use the maximum allowable speed to calculate for the angle. And when they do that, drivers can make that go on that speed, within that curve or stretch of road without skidding. So speed is independent of friction, but the speed is dependent on the banking angle and the radius of the road. That's it. So when a road is banked, one of the other advantages is that speed is independent of friction, but it simply depends on the banking angle. So where the road is banked, as drivers enter into that section or portion of road, as road safety, there is maximum speed sign, okay, mounted there, so that as you enter within, you know the speed limit. This speed, if the road is not banned, cannot be moved. Drivers cannot move on that speed if the road is banned. This is the advantage of banked roads. Please, is there any question? Class, is there any question?
No, please.
All right. So that's the advantages, okay, of banking. So if the road is banked, this is the formula for determining the maximum speed. RG tan of theta. And it's not different from the motorist making the turn. Because for cars, you can't turn your body to make that. That is why we have this. Okay. So that is just the difference. Now, what if the road is clear? There is no rain, there is no snow. Of course, there will be friction. So when there is friction, how do we also determine the maximum speed? So take notes. Let's quickly do that for when there is friction. Meaning when there is friction and the road is banked, of course, all the two actors are there. So how will the expression for the velocity, maximum allowed velocity be? Are you people there? Today you don't ask questions. Eh?
Please, we are here.
Okay. So a quick sketch again. When there is friction and the road is banked, that is what we are going to look at. So the road is tilted, there's a banking angle, theta. This is my beautiful car. The car actually look like the Pragya cars we have now. So the weight of the car is here. Mg. The normal reaction is perpendicular to the surface, the road surface. And if we extend this line, we have this angle, the banking angle equal to this angle here. We resolve this, got n cos theta. When we resolve this, this component must be perpendicular to n cos theta. So n sin theta. As the car moves within the curve, the centrifugal force tries to skid off the car from the circular path in this direction. And because there is friction also on the road, the frictional force would act in the opposite direction too. the centrifugal force. And so we have, this is friction. A force pulling the car off the circular track or path, and then frictional force also tries to keep the car in. So over here we have, yes, centrifugal force is a false force. I know. A river, okay, but that is why we have a river. Your question.
Mr. Eddie, I'm not asking about centrifugal force.
I know. Also.
I'm asking that why is it that the force, is it where the frictional force is? Why is the n sine theta rather not there? So that the frictional force will now act like
the
at the opposite.
The frictional force is on the surface of the road. And don't forget, this is the road though. The inclined plane. So if this is O, this is A, this is B. OA is the length of the road. You can say width, but I'm not calling it the width because I earlier said even OB is the width. So the frictional force is on the surface of the road due to the nature of the road. That is why I'm bringing the frictional force along the inclined plane. Are you okay?
Yes, please.
Okay. So because of, when you look at this, frictional force is along the road. It is also making an angle this with the n sine theta. And this angle is also created due to the level of the banking angle theta. So if it is bank theta, this angle would also be theta. The turning thing is happening because of the angle. Or if this is not there, okay, we'll have the normal reaction and directly balancing the weight. But because of the tilting of the road, that is why we have the angles. So if this is theta, this angle between the frictional force and n sine theta will also be theta. Okay. So it also means that we have frictional force also acting at an angle theta due to the angle of tilt theta. So frictional force is here as a hypotenuse. So when we resolve the frictional force, we'll have its horizontal component along this. So F cos theta. Its vertical component, which will be perpendicular to F cos theta, we want to bring it here instead of equal vector. So instead of having it here, we are bringing it along the car. And so that would also act here. This is F sine theta. So F cos theta, which is the horizontal component of the frictional force, F sine theta, which is also the vertical component of the frictional force, as a result of the angle tilt. Please, are we okay with the component of friction? Hello? Okay, now we are looking at sum of forces horizontally, sum of forces vertically. On the car, we have the n cos theta component of the normal reaction equal to these two forces, mg plus f sine theta. Then horizontally, we have n sine theta plus f cos theta, also without a balancer. But because they all act towards the center of the circle, we equate this to the centripetal force mv squared over R. Okay. Now, frictional force, F, is equal to the coefficient of static friction due to the nature of the surface, mu. However,
Mr. Adria, please, can you explain why the N cos theta is equal to mg plus F
oh,
sin?
we are looking at sum of vertical forces. When you look at this force going up, it is
Okay.
balanced by what is going down. So that's why.
Yes, please.
Okay. So if F is equal to coefficient of friction times the normal reaction, and normal reaction here is mg, let's substitute this for F. So we have N cos theta plus mg plus mg let me take my time, else you'll be crying at home. So F is mu mg sine theta. I'm just substituting this for F. Okay, I'm just substituting this for F. Are we there?
Yes, please.
Or better still, I think I'm even overdoing it. Let's use F n mu n. Okay, because we have normal reaction there. Let's substitute mu n instead of expanding it. So all that I'm saying is that this is n cos theta is equal to mg plus mu n sine theta. And when we group like them, we have n out, cos theta in, minus mu sine theta, which is equal to mg. I'm just taking where I have nn to one side of the equation. And this is my equation. Let's call this 2. It is a modification of equation 1 though. When we substitute F into equation 2, we have n sine theta plus mu n cos theta, which is also equal to mv squared over r. When we pull n out, we have sine theta plus mu cos theta, bracket close, is equal to mv squared over r. This is equation 3. Okay, let's divide equation 3 by equation 2. These things, they are not difficult. When you follow, you can derive it yourself. So divide equation 3 by 2. So we have n canceling out. So we have sine of theta plus mu cos theta equal to mv squared over r, all divided by equation 2, which is cos theta minus mu sine theta all divided by mg. Okay, M will cancel out. So we have this. We'll finish soon. V squared over RG. Now divide every numerator and denominator, every entity in there, divide through by sine theta. So we are going to divide every term by sine theta. When we do that, we have sine theta, no, rather cos theta. Sorry. We are dividing through by cos theta instead. And you will later understand why it is cos and not sine. So divide through by cos theta. We have sine theta divided by cos theta. Please, both numerator and denominator. Mu cos theta divided by cos theta, all divided by cos theta divided by cos theta, minus mu sine theta also divided by cos theta. And when you divide through like this, it is equal to doing nothing to the equation because both numerator and denominator will cancel out. So this is equal to V squared over RG. This side is equal to tan theta plus mu divided by, here's a reference.
Mr. Edia, please, why didn't we divide the V squared on RG by the cos theta?
So we just want to change sine cos to tan. So if we divide numerator and denominator by, it is like multiplying through by 1 cos theta, up and down. So it is equal as doing nothing to the left-hand side equation. That is why we didn't apply it to the right-hand side. Okay.
Yes, please.
So the denominator would be 1 minus mu tan theta is equal to V squared on RG. And when you rearrange, you have RG times mu plus tan theta over 1 minus mu tan theta is equal to V squared. And when you take the square root of V, you have R square root of square root of RG times mu plus tan theta over 1 minus mu times tan of theta, bracket close. So whenever there is friction and the road is banked, this is the expression for the maximum velocity. With this, the speed depends on friction mu, the nature of the road mu, and also depends on the banking angle theta. So this is the maximum speed whenever there's friction and the road is banged. And whenever there is no friction, the maximum speed is actually equal to square root of Rg tan theta. That is the problem of the day. So if there is friction and the road is banged, you must actually take care of all of them. You must take care of, and the maximum speed is determined by this amount. Okay. Class, is that okay? So just go write it step by step. You can easily prove this equation for both. You can easily prove it. It's not difficult. It's not difficult at all. Are you done writing?
Yes, please.
Can I move on? So I'll send you questions. We'll solve questions tomorrow. But I want us to move on to another area which is similar to this, and that is the conical pendulum. Conical pendulum. Another kind of horizontal circular motion. Another kind of horizontal circular motion. The conical pendulum. I'm coming. I want to share something with you on conical pendulum. How it looks like. I think we are used to simple pendulum. The simple pendulum. So look at the conical pendulum. So, okay, so it just look like a simple pendulum. A simple pendulum is a weightless string or a string with a very negligible mass with a definite mass, usually in a form of metal ball attached to. For a simple pendulum, it oscillates to and fro for a simple pendulum. I don't know if I have that of a simple pendulum here. I'm sure you've seen one before, but good. I have a simple pendulum over here. So he will demonstrate.
Hi, I'm going to show you some clips of motions, and can you tell me what is common to all the motions shown here?
So this is
That's right.
seesaw.
These are all examples of periodic motion. Periodic motion, simple pendulum.
Good. This is a
The simple pendulum is like a swing. Its motion is periodic in nature. The simple
from-
pendulum's motion is also
to-
called oscillatory motion
from.
since it moves
Okay.
to and fro. A simple pendulum is made from a small metal ball called a bob, and it
Yes.
is suspended by a long thread from a rigid support.
So
We can
mass
pull the
of
bob
string
and make
is negligible. So this is the picture of the simple, the motion of a simple pendulum. The conical pendulum is just like the simple pendulum. The only difference is that for a conical pendulum, the oscillation is at an angle. So it is tilted at an angle from the vertical. For simple pendulum, it moves just to and fro. Okay, you displace it, but for conical pendulum, it is displaced at an angle. And so it oscillates and then the string cuts the shape of a cone. That is why we call it as conical pendulum. It derives its name because the string always cuts the shape of a cone. Please, are we okay with conical pendulum?
Yes, please.